Hello everyone. So in this lecture, I want to go through more details of large-eddy simulations and kind of explain the equations that we solve and why we are doing that, so you get familiar with one of these important computational fluid dynamics techniques that we discussed in the previous session. Okay, so in order to refresh your mind, I want to give another detail what is the difference between DNS and LES. So in direct numerical simulation, so in DNS or direct numerical simulation, we resolve the velocity field on length scales down to the Kolmogorov microscale. So the grid's resolution is very, very high. So the velocity field is resolved on length scales down to Kolmogorov microscale or ETA, right? So the grid resolutions are very, very small. And as I said, in the case of atmosphere, they can be about 1 millimeter or less than that, okay? So these are very computationally inefficient. They are very computationally expensive methods. So we talked that we have an alternative to that, which is LES or large-eddy simulation. So in LES, we increase the grid size. So in our computations in LES, and then we do a low-pass filter operation. So a low-pass filtering operation is performed. So for the whole velocity field, we filter it with a low-pass filter, and only we resolve the velocities that are smaller than that filter size, which can be your grid size, which is typically set as your grid size. So only the filtered velocity field is resolved. And anything smaller than that filter size, grid filter size, is kind of modeled. So that's the premise and basis of the large-eddy simulation. So now let's look at this filtering operation, like how this filtering operation is done and how does this impact the equations and what are the equations that we actually solve in large-eddy simulations. So let's get started. The first one I want to talk about is filtering operation. So we define the resolved field, the resolved velocity field, or in general resolved field, it could be also anything. We define it as this, so U, and then we show it with this tilde. So U tilde at any point x and time, we define this resolved field or this filtered field by applying this filter G to all the velocities at every point. So G is our filter, low-pass filter, GRX, and then we apply to U the velocity X minus R and time and dr, the distance at any location. So we apply this filter in the entire domain, and where filter function, this filter function has to have a property. So where the filter function G satisfies this condition, that if you integrate it, G Rx dr, the integral of this over the whole domain should be 1. Okay, so this is the kind of filtering operation that we define in large-eddy simulations. And now let's see what are these actually, what are these filters, okay? So let's go a little bit further and see what are these filters. But before that, I want to see, I want to show that actually by this filtering operation, what we are doing is actually we are decomposing the velocity field. So the velocity field is decomposed to the following. So UI. So let me show it after that how the velocity field is decomposed. But before that, I want to talk about the residual velocity or residual field. So here we had the result field, and now I want to talk about the residual field. The residual field is the field that we are actually modeling. We are not resolving, okay? So it's like UI prime. Let me add also I here, because this can be for any velocity component. We do this. So UI prime is defined as the residual velocity field, x and t, which is going to be the actual velocity field that we had, UI x and t, minus the filtered velocity, the result velocity field, which is UI hat or tilde x and t. So this is the original one, and then this is the result one that we resolve at each time step. And this will give us this residual field here. So this means that the velocity field is decomposed according to this UI xt. The velocity field is decomposed into a filtered velocity UI hat, filtered result velocity, and unresolved residual velocity, U prime I. So this is resolved. So we resolve it at every time step, but we model this part of the velocity, which is unresolved. And this is typically smaller than the grid filter size, okay? So as you see, this very looks like the Reynolds decomposition. However, it has some differences. So this appears to be analogous to the Reynolds decomposition, but here U tilde, first of all, this result velocity or U tilde is not actually the average, is not actually U bar. It is a velocity field, a result velocity field that is kind of obtained through this filtering operation, okay? And so when this is not U bar, when U tilde is not U bar, similarly, U prime, if we take the tilde of the U prime field, so in the unresolved field or residual field, if we do the filtering operation here, right, by doing this integral here as we showed here, so this is not going to be necessarily 0, unlike u prime bar, which we know it is 0 in general. We can have some cases that becomes 0, but in general, this is not the case. Okay, so these are two main differences of this filtering operation with the Reynolds decomposition. So in Reynolds, we were just kind of decomposing the velocity into a mean velocity and fluctuating part, but here we are decomposing the velocity field into a resolved part and unresolved part. And resolved part is actually the filtered velocity and then the residual field that remains after that filtering. Okay. So these are two main differences of this. So you shouldn't kind of think that they are actually the same, and there are some differences between them. And some filters, so that you know what actually these filters are. So we can do this filtering by any filter. So we have lots of options, and depending on the LES that you do, you can choose these different filters. But some of the famous ones are here. One is Gaussian filter. So Gaussian filter, the function GR is actually 6 over pi delta squared to power 1/2 e to the minus 6r squared over delta squared. And delta is just grid size. Okay. So let's say here we have the grids that we are resolving. In a flow, and delta would be just a grid size. That we do this filtering operation on. So anything greater than this grid filter size, any eddy is resolved, like these eddies are all resolved, but any eddy that is smaller than this grid filter size, like these eddies, will be modeled. Okay. So the second filter is sharp spectral filter. So this filter is simple, a little bit simpler. It's sine pi r over delta over pi r. So you just take the integral of this by multiplying this with the velocity field. And there are also other filters like box filter and other filters that you can take a look at them yourself. So this was just so you get some kind of you get more familiar with this kind of filters that we are using. Okay. So after doing this filtering operation, what we do in large-eddy simulation is that we do this filtering operation on the momentum and continuity equation, and then we get the filtered equations that we are going to resolve. So let's see the first filtered momentum equation, and this is actually going to be the governing equation in LES, and that's what we are going to actually solve at every time step numerically. Okay, so if you apply this filter into the velocity field and into the momentum equation, what we are going to get is this equation, which is the filtered momentum equation. So partial ui tilde over partial t plus uj tilde partial ui tilde partial xj equals to minus 1 rho partial p partial xi minus partial over partial xj. So the first one is the filter pressure. The second one is tau ij. And then the third one is the viscous forces nu, partial square ui over partial xj square. And then you can have other terms like gravity that I'm not going to write, or Coriolis force and other forces that you have in your flow. But this is kind of the basic filter momentum equation. So this is actually going to be the governing equation in our LES, but typically it is common to remove the trace from tau ij and place it in the pressure term. So what we typically do to kind of simplify this is we define this tau ij R which is residual stress, which we subtract from tau ij its trace. It's the trace on the matrix. If you have this matrix, the trace is here. So we subtract that minus 1/3 tau kk delta ij, which is the Kronecker delta. And then we define this modified pressure, which is actually 1 over rho of the filtered pressure plus 1/3 of tau kk delta ij. So we subtract that trace from here, and then we add it to the pressure term. So this is typically done in large-eddy simulations. And then this will be our revised momentum equation, revised filtered momentum equation, which is going to be, let me copy this. Everything is kind of similar. We just change the pressure and the tau ij is going to be the residual stress, and this is modified pressure plus nu partial ui partial xj squared. Okay, so this is actually our governing equation in LES. We actually resolve the velocity field by, at every time step, by kind of integrating this equation in time and calculating all the terms. Okay, so it has some tricks that, for example, we want to also, for example, for incompressible flows, we want to also solve this continuity equation, the continuity equation. So we want to kind of force this equation to the velocity field to also be divergence free. So I'm not going to go through those details, but this is kind of the overall approach and overall governing equation that we have in large-eddy simulations. But in order to close this equation, we need a model for this tau ij. We don't know that, right? In terms of the velocity components, right? So there are some unknowns here. One is p pressure, and then the other one is tau ij, and we want to know ui, the velocity field at every time step. So in order to close this equation, we need to know what is this tau, what is this residual stress term. So we need to actually bring another model for these LESs. Unlike the DNS, which we don't need this, for LES we need this. So one of the famous models for for this for modeling this tau ij in LES community is known as the Smagorinsky model. So the Smagorinsky model is defined as this. So to close the equations for the filtered velocity and model for the residual stress tensor tau ijr is needed. And one of the famous one is again this Smagorinsky model, which actually models this as tau ij equals to, based on the strain rate tensor, so it models it at -2 times nu t, which is the eddy viscosity, times the filtered strain rate tensor Sij. Okay, and this is eddy viscosity. Okay, so we can also model eddy viscosity using the mixing length hypothesis, which I didn't go through, but this is basically one way to model eddy viscosity, mixing length hypothesis. So based on this hypothesis, we can say that nu t can be length scale squared times a characteristic filtered rate of strain rate, the absolute rate of that strain rate, okay? And again, this Sij is, the tau ij to nu t Sij is kind of similar to that concept of stress that we had in the earlier classes, like the eddy viscosity times the du over dx, right? It's kind of similar to that concept, but now we do it with these strain rates instead of that, okay? So this is actually the strain rate, if you don't remember, is minus nu t partial is going to be partial ui over partial xj plus partial uj over partial xi, okay? So it's actually like this mu times partial u partial x that we had in the viscous flows that we talked about in the earlier lecture. So it's actually similar to that, using the same idea. And here nu is the eddy viscosity, nu t is the eddy viscosity, and Ls is Smagorinsky length scale, Smagorinsky length scale, and S is characteristic filtered rate of strain, which is actually square root of 2 Sij tilde Sij tilde. Okay. And LS, this Smagorinsky length scale, is kind of proportional to the grid size delta. And so we write this as LS equals to CS times delta, where CS is the Smagorinsky constant. Okay. And so based on this, we can define a final nu T to model that with this CS delta squared from here times this S. And that will close our equation. So because here we have nu tau and here we have nu T. And we know that in general, this Smagorinsky coefficient, which is LS over delta, is typically around 0.17, but this can be found in different flows with another way or another mechanism. So as you see now, we have closed our equations. We have closed this stress term, showing it based on these velocity components, and also nu T also based on this velocity component Sij. So everything is now for tau, the residual stress is based on this velocity components Ui. And so now we have the only unknown is this pressure, which we can find it by forcing the velocity field to be divergence free. So by adding another equation, partial Ui, so we can find it like by trial and error, find some P pressure, and then by forcing it to be divergence free, then we can find the actual pressure here in the system. And so this will close our equations. So just final note that this CS, the Smagorinsky coefficient, or the Smagorinsky constant, can be found if it is just, we set it as one number. This method is called static Smagorinsky, and if we just change it based on the flow types and based on the different flow situations, it's kind of called dynamic Smagorinsky. And nowadays we usually use dynamic Smagorinsky models because they are more accurate. And so there are many methods to kind of find this Smagorinsky coefficient of constant based on the flows that I'm not going to go through them. So there are lots of research on this subgrid scale modeling or subfilter stress modeling. Okay, so this is actually called, if I forgot to say that, it is subgrid scale or SGS model. It's one type of subgrid scale model, right? Smagorinsky model. Okay, so this kind of an overview of large-eddy simulation and how we do that. So what we actually do is we do a filtering operation over the velocity field, where the filter is kind of analogous to the Reynolds decomposition, but it's not exactly the same. And the filters can be anything like Gaussian filter, spectral filter, sharp spectral filter. So we get the filter momentum equation, and then the only we do some revisions to kind of put the trace of the matrix into the modified pressure, because the way it is, then we are going to have the pressure. We can kind of model this pressure term using the subgrid scale models. So now in this revised filter momentum equation, because we got rid of the trace, which is kind of similar to the pressure, like the trace of the stress tensor. So we got rid of that. So we only have a trace free, or the residual stress tensor, where we can kind of model that using this eddy viscosity, using these different subgrid scale models. And one of them is Smagorinsky model, which I explained it here, based on this nu T times Sij. We can model that. And then for Nuti, we can use the mixing length hypothesis, and then this will be our model for Nuti, where CS is the Smagorinsky coefficient constant, which is typically 0.17, but then you can also modify it and find the optimal value based on your simulation. And so now our equations are closed, and we can kind of solve this equation for any high Reynolds number flows. Thank you very much, everyone.